We're going to move on now to the second talk of the afternoon by Patricia Gonçalves from Lisbon, who's going to speak about non-equilibrium fluctuations for the slow boundary symmetric exclusion.
Thank you very much. I'm just drawing a picture. I'm sorry. I will finish very quickly. Okay. Okay, so thank you very much, and I also want to thank the organizers for the invitation for being here. So I'm going to introduce a very simple model with dynamics. I think you can all see. Can you all see that blackboard over there? No? Oh, sorry. What can I do? Okay, you will see the pictures. I'm very sorry. I thought you could see it. Anyway, it's a very simple model. And it was also discussed today in the talk of Giovanni. So it's the symmetric simple exclusion process, which is in contact with reservoirs. And the idea is the following. So this is a joint work with Tertuliano Franco, Milton Hara, who is here in the audience somewhere, and Adriana Neumann and Otávio Menezes. So the model is like this. We have a discrete set of points. Let me call it lambda n, which is this set of points 1, 2, 3 up to n minus 1. In each one of these points, we can have at most one particle, so at one particle per site, and we put it in contact with reservoirs. So let's say artificially we put 2 points, let's say at 0 and at n, which are representing reservoirs. So particles can get in and get out from the system through these points. Okay. So the dynamics is like this. Whenever we have a ring of, so there are some Poisson processes between each consecutive pair of sides, and whenever you see a mark of a Poisson process, the particle decides to jump to the position which is connecting the two sides. Okay, so if I see a clock, let's say if I see a ring of a clock, the particle jumps to the nearest neighbor position, and with symmetric rates. So to go to the right at rate 1 and to go to the left at rate 1. But so this is the exclusion process. So it means that if the destination site is already occupied, the particle doesn't move. It stays where it is. Okay? At the boundaries, what happens is the following. So particles now can be injected, for example, from the left boundary, so from the site 0 to the site 1, with a rate. So here it's written k alpha over n theta, and I will show you what is the role of all, because there will be a bunch of parameters. We will have alpha, beta, kappa, and theta. Okay, n is the scaling parameter. Alpha and beta, they are kind of regulating the density at the boundary. So from the left boundary, I get into the system at this rate, kappa alpha over n theta, and particles get out from the position 1 at rate 1 minus alpha kappa over n theta, and the same thing at the right, but you just replace alpha by beta. Okay? So if, for example, alpha is very close to 0 and beta is very close to 1, we will have particles coming from the right and leaving from the left. Okay? Is it clear, the dynamics? Yeah? So my idea is to tell you, so I will discuss in the beginning, okay, first I will show you some pictures about these dynamics. So we have this. I'm not sure you can see, there is some arrows, some, let's say some lines here. Can you see them in blue? So this means that the clock rings and the particles decides to jump. So for example, in this case, this clock is ringing, the particle is going to jump to the right because it's empty. And then we wait another ring of a clock, so this is what happens after. So now if we see, for example, this clock ringing here means that a particle can come from the left reservoir to the site 1 because it's empty, and that's what happens. And the same thing here at the right. So if we see this clock here, then a particle can get in and it jumps over there. Okay, is it clear? Yeah? So now, okay, just to explain and to put all the notation that I need. So lambda n is going to be called the bulk. So let me put here, this is the bulk. I have my state space for this Markov process, which is this omega n. So let's say at each site of lambda n, I have either a 0 or a 1. If I have a 1, means that I have a particle at the site x. If I have a 0, means that the site is empty. The infinitesimal generator is a sum of 2 generators. Oops. So we have this part here, which is telling me what happens in the bulk, and this part here is telling me what happens at the boundary. So here, so let me explain what this notation means. So this is just the way so I take a function f, a function of the dynamics, and this configuration here, eta x, comma x plus 1, is the following. If I have a configuration eta, the configuration eta x, x plus 1, so this one, so suppose I have eta, this configuration is just swapping the value of the part of the configuration at the point x and x plus 1. So for example, if my eta was something like this, 1, 1, 0, whatever, and this is x and this is x plus 1, so this one would be 0, 1, 0, 1, 0, and so on, okay? So it just swaps the occupation variables at x and x plus 1. So this is the bulk dynamics, and now let's see the boundary dynamics. So let's just look at x equal to 1. So this is going to be the left boundary dynamics, okay? So what is written here, so okay, so before, let me explain what is this eta of x. So if we have now the configuration eta, eta of x, so eta at 1, I'm looking at x equal to 1, is just doing the following. It is flipping the value of the configuration at the site 1. So for example, if it is this configuration here, so eta of 1, I'm not sure you can see here, probably not. Can you see here? Kind of? Okay. So eta of 1 for this configuration, you just swap, so you flip the value of the configuration, so it's going to be 1, and then the rest continues the same. So 1, 0, 0. So this guy, this transformation, let's say, it exchanges the configuration only at one site, while this transformation here, eta x, x plus 1, it changes the value of configuration in two sites, okay? So what are the rates at the boundary? So let me explain what these rates mean. So let's look at x equal to 1, means that my R1 is equal to alpha. So I'm looking at the left rate, at the left boundary. So this means the following, oops, here. So I have alpha 1 times 1 minus eta of 1. So this means, so 1 minus eta of 1 means that it is non-zero if eta of 1 is equal to 0, right? Because I have 1 minus 0. So this means that the rate is given by alpha, so it is the entrance rate, right? And here on this side I have 1 minus alpha times eta of 1. So this is non-zero if eta of 1 is equal to 1, and the rate is 1 minus alpha. So it means that the particle can get out at this rate, okay? So the kappa over n theta is in front of it is here, it's in front of everything. So I just multiply by it, okay? So now, what I want just to, the goal of the talk is to, let's see, to change the value of this parameter here, this theta. So a first observation is the following. This is my microscopic model, and we have these parameters alpha, beta, kappa, and theta. And at the macroscopic level, so when I want to, let's say, to see what are the PDEs, which are telling me how is the evolution of the density of particles, this parameter kappa will not appear in all the, let's say, it will only appear in a certain regime of theta. So my goal in this talk is to explain to you what is the impact at the macroscopic level by changing the value of this parameter theta. So suppose the theta is very, very big but positive. So this means that the reservoirs are very, very slow. On the other hand, if theta is negative, it means that the reservoirs are very, very fast. So the idea is to try to see what happens to the macroscopic system, to the macroscopic PDE, by changing this value of theta. Okay, so that is my goal. So this is what I want to show you. And okay, so the first question that we ask is what are the invariant measures for this system? So we put the system in contact with the reservoirs, and now we ask what are the invariant measures? So this means what? An invariant measure means that I start my system, so my eta at 0, let's say my initial configuration, let me call it, okay, so here 0 means at time 0, and it has a certain distribution, let's call it mu n, and now I let the system evolve in time, and I ask what is the distribution of eta of t. So if mu n is preserved by the evolution, it is an invariant measure, okay? So what we can show, and it's not difficult to just write it down, it's not difficult to find it out, is that when alpha is equal to beta and equal to rho, So let's say the intensity of the reservoirs is exactly the same, okay, so alpha is equal to beta. The Bernoulli product measures, they are invariant measures, okay? So Bernoulli product measures means that when you look at the occupation site at x, so the eta of x, the random variable eta of x, it is Bernoulli and with parameter rho, okay? But when alpha is different from beta, so when there is this current of particles, so suppose alpha very close to 0 and beta very close to 1, so there is this natural flux of particles from the right to the left, the Bernoulli product measures, they are no longer invariant measures. But there is a way which is called the matrix ansatz method, which consists in writing this invariant measure or the stationary measure in terms of products of matrices. And this gives us information about the, let's say, the properties of the stationary measure, okay? I will not use it here, but I will explain to you later on what can we get with this method, okay? So, anyway, just to make notation also, I'm going to fix now notation. Whenever you see alpha equal to beta equal to rho, we have this invariant measure, which is the Bernoulli product measure. When alpha is different from beta, we have a certain invariant measure, a certain stationary measure. We know that this measure exists. Okay, I didn't mention, you see it written here, because we have a Markov chain, which is irreducible, and with a finite space state. So we know that there is some invariant measure. And this matrix method gives us information about that measure, and I'm going to denote it by mu SS, okay, the stationary state. So now, what about hydrodynamics? So I want to explain, maybe I can go to the other side. So what do we mean by hydrodynamic limits? So is the first thing I want to discuss. Yes, it's okay. So we do the following. I fix a configuration eta, and I call to this measure here. So this is just a sum of Dirac measures. So this delta x over n is a Dirac measure at the point x over n. So I'm making, let's say, a scaling limit. So I have an interval, which is my macroscopic space. So the space 0, 1. And I take n, a scaling parameter. I split this interval into small intervals of size 1 over n. I just cut my finger, so I'm sorry, I'm doing this all the time. So 1 over 2, blah, blah, blah. And to which, so we associate to this interval a macroscopic, a microscopic point. So 1, 2, 3, blah, 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 n minus 1. Okay, so there is a relation between these two spaces. Whenever you take a point in here, u in 0, 1, you just get this in this space that we call the lambda n, okay? And when you have a point over here, if you want to get one over there, you just divide by n. Okay, so there is a relation between these two worlds, the macroscopic world and the microscopic world, where you have these dynamics. So the goal is to show the following. So suppose we don't have any reservoirs. Particles would be just moving around, I mean, on this discrete set. And the goal is, okay, the dynamics is only doing the following. It is moving particles either to the left or to the right. So the question is, how does the density of particles evolve? Now we have reservoirs, so the density of particles is no longer a conserved quantity. And what we want to, let's say, to extract is to see how can I get the evolution, so how can I derive, if I call this, sorry, rho Tu, the density, the density of particles. This is a solution to some PDE, and the question is, what is this PDE, and what are the boundary conditions for this PDE due to the, let's say, to the connection with the reservoirs. So let's see. In hydrodynamics, so what we define is what is called this empirical measure. So this measure is just giving weight 1 over n to each particle. Remember that this eta of x is just 0 or 1, right? So when it is 1, it is giving weight 1 over n to the particle at x. An important thing is that we have, since we have discretized space, we have to speed up the time. So we are going to speed up the time in this time scale. It's called the diffusive time scale, the Tn square over here. And there is an assumption. So we cannot start the system for any measure, so we have to impose some condition. And the condition that I'm going to mention now is what is called mu(n) to be associated to some profile. So what do? We fix a profile, just a function, rho 0, from 0, 1 to 0, 1, which is measurable. So later on I will have to impose something else. So, but we fix a profile which is measurable, and we say the following. You take a test function h, which is continuous in 0, 1, and you assume that this thing is true. So let me explain what does this limit means. So on the left-hand side here, this is just the integral of the test function with respect to this empirical measure. Okay, this is what is written here because this is a sum of Dirac measures, we get this. And on the right-hand side, this is just the integral with respect to a measure, which is absolutely continuous with respect to the Lebesgue measure, and with this density here, which is the profile that we fixed. So we assume that this is true. You start from a measure from which this convergence is true. So this is just telling us this is the weak convergence of the empirical measure at time 0 to this deterministic measure given by this, with this density rho 0. Okay? So we assume that this, let's say, this weak convergence is true at initial time. And the question is, if this is true at initial time, is it true at a later time t? So is it true that the empirical measure at time t converges to some deterministic measure, which is absolutely continuous with respect to the Lebesgue measure, and with this density rho t, where the rho t is solution, usually in the weak sense, to some PDE. Okay? So this is the first thing that we have to, that I will explain to you how one can derive this result. Is everything clear up to here? Is there any question? No? No? Okay. So, oops, sorry, what am I doing? Okay, so the first result, this was proved by Baldasso and some other co-authors, and the result is the following. In fact, the hydrodynamic limit is true in the case, so let me just start to put some restrictions on the parameters. So now theta is going to be greater or equal to 0, so we are in the slow case. And the result is the following. So in fact, it is true. So the previous result is true. If you assume this at initial time, then you have this convergence at time t. And rho t, the density, is the unique weak solution to the heat equation with different types of boundary conditions. So the boundary conditions are like this. When you take, so theta is the parameter which is here at the boundaries, right? So when theta is less than 1, so means that the system, the boundaries are slowed, but I mean they are very, you can take, for example, theta equal to 0. So what we get is Dirichlet boundary conditions. It means that you have a solution, a weak solution to the heat equation with Dirichlet boundary conditions. Your profile is alpha and beta at the boundaries. When alpha is equal to 1, what we get is the heat equation but with Robin boundary conditions. So now the profile is no longer alpha and beta at the boundaries, but we have a control, let's say, on the derivatives at 0 and at 1. And the derivative of 0, this is, let's say, proportional to the difference between the density in the bulk and the density at the boundary. Okay? So this is why it is rho 0 minus alpha. And you see that kappa here, so kappa does not appear here, but it is, I mean, it is present in the microscopic model. It does not appear in the case theta less than 1. It appears in this case, in the Robin case. And when theta is bigger than 1, we just get Neumann boundary conditions. Okay, so the system is very, very slow. And again, we do not see the dependence on kappa at the macroscopic level. Okay? One important thing is that, in fact, in the hydrodynamics, this is proved now, is that in fact we can take the case theta negative. So remember that theta negative is the case where the boundaries are very, very fast. And in fact, this regime is also true. The only difference, I mean, in the proof, so let's say the result is exactly the same. You can take theta negative and you get again Dirichlet boundary conditions. The only thing which is different in the proof is that we have to take different space of test functions and different notions of weak solutions to the heat equation with these Dirichlet boundary conditions. Okay? Any question? No? Okay, so now, okay, so before I go on, now we ask, okay, very good. So now I know how to show hydrodynamics starting from this measure, which is associated to some profile, whatever is a measurable profile that I fix, and if I assume this, then I know that the result is true. So the question that we can ask is the following: is it true, this result, for the stationary measure? This measure that we know nothing except if we use the matrix ansatz method. So what we have to do is to show that the stationary measure is in fact associated to some profile. Okay? And this can be done, this is what is called the hydrostatic limit. So if we denote by mu ss that stationary measure, that we know that it exists, we can show that this measure is associated in the sense that I mentioned to some profile, and this profile is in fact the stationary profile of the PDE, of the hydrodynamic equation. Okay, in the Neumann case, there is something which I have to point out, okay, before going to Neumann. So, Dirichlet case, the stationary solution of the heat equation with Dirichlet boundary condition is just a linear profile connecting alpha to beta. In the Robin case is again linear, but it's connecting not alpha to beta, but some combination of alpha and beta. And in the Neumann case, so the Neumann case is where we have the derivatives equal to 0, any constant solution is a stationary solution. But the system equilibrates exactly to this solution, to alpha plus beta over 2. So let's say the middle point between the intensity of the reservoirs. Okay? And it's possible to show that in fact the stationary measure is associated to this stationary profile. So this is a way that one can try to have, let's say, a guess about what type of PDE one can get and what type of boundary conditions one can get, is to look at this to the stationary measure. So just before I go on, because I want to reach fluctuations, so how to prove this? This is classical in the theory of stochastic processes. What we do is that we show tightness of some sequence of measures, and then we characterize the limiting point by showing that it is unique. And what is fundamental, and sometimes is the hard part, is to, let's say, to cook up a notion of a weak solution to some PDE and to show that it is unique. Okay? This is sometimes the hard part of the program. Tightness usually is something which is simple. Okay, not always, but usually it is. But let's say formulating the notion of a weak solution, and we have to prove exactly that from the particle system, and then showing that whatever is that you formulate as a weak solution has a unique, is unique, let's say. Okay, so this is more or less the idea on how to derive these results, these, let's say, these hydrodynamic limits. So before going on, one simple thing that one can do, there is no, this slide, okay, it's a bit ugly, but it's very simple to do the following. If we get, for example, an exclusion process like this, and we want to try to guess what are the boundary conditions, and we know nothing, one thing that we can do is to compute this function. So let me explain what this is. So mu n is any measure. We start with any measure. We do not impose any condition on it. And we compute here the expectation of the occupation site at x. And we call this function rho ntx. Okay, we have, so remember that the eta is a configuration in a configuration of the system. So it only makes sense to talk about eta at 1, eta at 2, etc., eta at n minus 1. So what we do is that, let's say, we make a convention saying that eta at 0 is alpha and eta at n is beta, the intensity of the reservoirs. So then we have this definition, because if eta of 0 is alpha, then rho at 0 is alpha and rho at n is beta. And we do some simple computation using the Kolmogorov's-Fordworth equation, and we get a discrete equation for this function rho n t of x. So let's look at this operator here. So what I say is that, okay, we can compute these, the action of the generator is in here, and this operator Bn is kind of, it's almost, let's say, a discrete Laplacian. So everywhere between 2 and n minus 2, what we have here is a discrete Laplacian. But at the boundaries, there is something which is, let's say, different, right? I have this, so imagine that theta is equal to 0 and kappa is equal to 1. So I get exactly a discrete Laplacian everywhere, okay? So this is the reason, okay, it is a way for us to see what are the boundary conditions, let's say naively, is to do the following. If you take, for example, so let's think about the Robin case. If you take theta equal to 1, the factor that you have here is k times n. What you have here is an n square. So you can do a Taylor expansion and write a term of order n in here times the derivative of your function. And here you have kappa times n times the jump of your function, times, let's say, the difference at 0, and here you have to look at this as if it was macroscopic, so 1 over n. So what it's telling us is that if I want to eliminate this factor of order n, I need to take these boundary conditions of Robin type. The derivative is equal to kappa times the difference of the value of the function at the reservoir and at the bulk and at the boundary. Okay? So this is more, let's say, a way to try to see or try to guess what are the boundary conditions. Okay? Is it okay? Is there any question? No? No? Okay, so now I want just to, before going to fluctuations, so let me just explain. Okay, so we have this equation here. This is a discrete equation, this one here. And we can compute the stationary solution for this equation. So we can make this computation and check that it is exactly linear, given by this anx plus bn. And it's not difficult to show that, in fact, this discrete, I mean, this what we call the empirical profile, it is close, I mean, it converges to the stationary solution of the PDE, which we have seen before what it was. So it converges to this function rho bar, which is just a stationary solution of the hydrodynamic equation. Okay, so now fluctuations. So now I'm going to explain to you what happens in at the fluctuations level. So now we say, okay, my system is not on top of this, let's say, of this hydrodynamical profile, so I want to see how it fluctuates around this profile. So let's try to see how does the system behaves and what is the impact of changing this value of theta at the level of the fluctuations. Okay? So before in hydrodynamic limits I said, okay, I have an empirical measure, so what can I write here or there? Can I write here? Yeah? So in the hydrodynamic limit, we have an empirical measure like this. Oops. 1 over n or 1 n minus 1, doesn't matter. X goes from 1 to n minus 1. du eta tn square of x. And we proved, so I mean, one can prove that this empirical measure converges to a deterministic measure in which this density is solution to some PDE in the weak sense. So now I'm going to define what is called, which is written down here. So this is called density fluctuation field. So I take a function, okay, not f, h, sorry. I take a function h and I'm going to explain to you where does this function lives, and leaving means it will depend on the range of the parameter theta. So depending on the value of theta, this parameter here, I will have to choose different space of test functions. And how do I define these guys like this? So you can see the definition here, but it is like this. I integrate a function with respect to this empirical measure. When I integrate, okay, maybe I can write it here. Is it okay if I do this? You agree? Yes, I just integrate h with this. And now I do. Okay, so now I put this guy here. So I have 1 over n, the sum of x, h, x over n, times eta. I'm not sure everybody can see this. Maybe not. Yes? Can you see? No? Yeah, you can see? Is it okay? Like
you can use the left blackboard.
Sorry?
You can use the left blackboard.
Yes, this one, no? Ah, the other one. Yes, I could erase the other one. Yeah, okay. So I erase this one. So now I have the integral of h with respect to the pi and t. This is just 1 over n, sum over x, eta t n square. Everybody agrees with this? Yeah? Now I take the expectation with respect to this measure that I am fixing, and I'm not going to impose anything on mu n by now. So the expectation with respect to mu n of this is going to be, so I'm going to put the expectation in here, and this is exactly what we defined as rho and t of x in the previous slides. So now I do the following. So my density fluctuation field is just the difference between the integral, so this integral minus the average of the integral, So at the end I have these. And I take the central limit scaling, so here I have 1 over square root of n. Okay, so this is what is called the density fluctuation field. And what we want to prove, so this is a random distribution, and I want to show that it converges in some sense to yt, which is solution to some stochastic PDE. Okay? So this is the question that I want to answer now. So let's see. So before we go on, we have the definition of the density fluctuation field. Is there a clock? Yes, there is a clock. Ah, yes, okay, good. So then we say, okay, I have to tell you where these test functions age, where they live. So I define, where is this? Ah, yes, it's here. So I define the following set of functions. I'm going to denote it by this letter S of theta, but in fact we only have 3 spaces. So so let me make probably another drawing. Can you see here? No? Yeah. Okay, here. Can everybody see here? Yeah. Yeah? Good. Maybe not with this color. You tell me. You can see? No. It was not a good choice. Sorry. So here I have, just to make it big, so theta equal to 1. This is the Robin case, so I'm just reminding the picture that I've shown to you in the hydrodynamic limits. So this is the Robin case. Yes, yellow. The Neumann case. And the Dirichlet case. Everywhere here. So for each one of, so we only have 3 regimes, either Dirichlet, either Robin, either Neumann. Robin is the one which is the critical one connecting the 2. So I'm going to define this S of theta, but in fact, as I say, there are only 3 spaces. So for theta less than 1, the space of test functions is such, so what we have is functions which are C infinity in 0, 1, plus, now I never know, odd or even. 2 is odd or even? I never know. Even. Okay, I always mix the 2, so I always ask. So all the even derivatives at 0 and at 1, they are equal, and they are equal to 0. Okay? For theta equal to 1, all the derivatives at 0 and at, sorry, there is a mistake. No, there is not mistake. All the even derivatives at 0, they are equal to the, no, sorry. Okay, you see what it's written. It's better. I don't say anything. I always mix. It's a mess. Anyway, this thing has to be satisfied. Okay. So think about h prime. H prime at 0 is equal to h at 0, and h prime at 1 is equal to minus h at 1. And then you take these to a upper level. And in the Neumann case, now it's the odd derivatives equal to 0 at 0 and 1. Okay. So we need this. So we take this. Three different space of test functions, and this is where I'm going to define the density fluctuation field. So I'm going to put now, so let me show you. I'm going to introduce these operators, which are basically, let's say, the Laplacian, let's say the macroscopic Laplacian, not the micro, the macroscopic Laplacian, let's say, but defined on this space S of theta, and the gradient here. I'm going to use these 2 notations, just indexed by theta, just by saying that they are defined on the space of test functions. And I'm going to denote by this letter t theta of t, and the semigroup associated to the hydrodynamic equations when we take, let's say, the homogeneous version, alpha equal to beta equal to 0. Okay, so you go to the PDEs, you take alpha equal to beta equal to 0, and you call t of theta the semigroup. Okay? So now, let's look first at the critical case. So now I'm going to look at the Robin case. So I'm here, I'm in the green line. So my space of test functions, so let's think about these. So the space of test functions, the S at 1. So sometimes you will see a 1 in these. The 1 means that we are restricted to the case theta equal to 1. Okay? So we have functions which are of class C infinity, And let's say h prime at 0 is h at 0, and h prime at 1 is equal to minus h at 1. So this is what I will need, but you know that I have more conditions on that. I have more conditions on the test functions. So now it comes. What are the initial measures? What do I need to impose? So remember that in the hydrodynamics, I need to impose that mu n was associated to some profile. I started from there. So let's see what do we need at the fluctuations level. So I say, okay, you take a measurable profile, again, some profile rho 0 from 0, 1 to 0, 1, and you assume that your initial measure mu n is associated to that profile. So this is the same story as in hydrodynamics. I'm not assuming anything more. So now I call to this, again, rho n 0 at x, the occupation at the site x at initial time. And the first thing that I need is that the distance between this function and this function, it goes to 0 with this order 1 over n. Okay? So this is something that we need. And we also define, let's say, the correlation function, the 2-point correlation function at time 0, like this. So what is written here is exactly the same as the expectation of eta x minus rho. Sorry, it's better to write it down. So what is written over there, where can I write now? Can I write here? Here? Yeah. So what is written over there is exactly, so phi n 0 at xy is the expectation of eta 0 at x minus rho n 0 at x. So it's the correlation, y minus rho n 0 at y. Okay? So we define this function, and what we need is, okay, one important thing about this function is that it is symmetric in the variables x and y. So in fact, in some couple of slides, you will see some set. So remember that I have the bulk. Everybody can see here? Kind of. So I have 1 n minus 1, my set lambda n, where I have the particles. But here, I'm kind of adding a new dimension. So here, this function is going to be defined. Let me draw it like this. So this is the line y equal to x plus 1. This is n minus 1. I'm not sure you will be able to see. No, Thierry, no. Okay, sorry. Okay, I will erase this. So this correlation function, so this function, rho n tx, the empirical profile, is living in here. 0, 1, 2, n minus 1, n. And here it's alpha, and here it's beta. Now we have a new function, which is this correlation function, that I am defining here only at the time 0. And it is living in this space. So let me see if I can draw it properly. This is n minus 1. This is let's say, not the diagonal, but y equal to x plus 1. This is n minus 1. Okay, sorry, this is supposed to be 1, okay? Okay, so this is my set. I'm going to call Vn. Is it clear, my drawing? Yeah? Yeah? Okay. So you see that, for example, if I define this function phi for x equal to y, what I get, if I do the computation, since my eta x squared is eta, is exactly, so let me write it here, my phi n 0. So this is the reason why I do not put the diagonal. This is just the expectation of eta x squared. So this is my, oh my god, rho n tx, 1 minus rho n tx. Is what is called the mobility computed at rho n tx. Okay? So the condition that we need, okay, we need mu associated to a profile, the same thing as in hydrodynamics. We need that the empirical profile at time 0 to be close to this profile rho 0 that we fixed, and close in this order, and we need that the initial correlations of the system, they go to 0 again with this order 1 over n, okay? And starting from this, Okay, first, let's see examples of initial measures because, I mean, we are putting some conditions, so let's see if there is some measure satisfying this. So if you take the measure mu n as the Bernoulli product measure given by this, so I mean your eta x is Bernoulli but with this parameter rho 0, then all the conditions are true. It's not if, I mean, correlations are 0. And if mu ss is the stationary measure, this measure that we know that we can have information from the matrix ansatz method, then again we can check that all the conditions are true, but we have to choose a special profile. You see, I say here that all the conditions are true, but the profile that I choose, this rho 0, has to be the stationary profile for the PD. Okay? Then it's simple to show that these measures, these stationary measures, they are associated to that profile. Okay, so the result is like this. This is like the most general result that we can prove, which says the following. Okay, there is tightness, and all the limit points, they satisfy this equality. So you take a test function. So here you see the one because I defined tt of theta, the semigroup. But this is for the case theta equal to 1. So we write all the limit points in this form. So here there is a space-time white noise. And what we have is, okay, there is this, okay, let me explain what this norm here is doing. So L2 is the usual L2 space. The one which is there, I'm going to write it probably here. Can I write here? Yes? No? 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 So I'm going to write in here. Okay, here. So this is just L2 theta of rho r. So the inner product in this space is given by this. So let me say who is chi at u is u, 1 minus u. Okay, it's just the variance of these variables eta x with respect to the Bernoulli measure with parameter u. So this is this, fu gu, this, sorry, du. Plus, in the Robin case, there is an extra term, which is like this. Alpha plus 1 minus 2 alpha, sorry, rho r 0, f at 0, g at 0. Plus the same thing if you replace the 0 by 1 and the alpha by beta. Okay, so there is something extra. Okay, so it's like you have an L2, let's say the L2 space, but with respect to the Lebesgue measure plus a Dirac at 0 and a Dirac at 1, okay, with this weight. Okay, so we have this result. One thing that, okay, this is tightness plus we know how the limit points behave, but we don't know how to show uniqueness. But if we have the condition that the initial field converges at time 0, then we have uniqueness and the solution, so let's say the limiting field is solution to this equation, so it is a Nornstein-Uhlenbeck process with these characteristic operators, this Laplacian and this gradient. So I'm going to skip them because I'm going to show you very similar results. So when you start from the Bernoulli product, I mean, when you start from your initial measure is a Bernoulli product measure, but with your eta x is Bernoulli with this parameter here, then the result is again true. And for the stationary, I mean, you take the stationary measure in which your alpha is different from beta, so you are not in the Bernoulli case, you are in the weird case. Again, we can show that, we can show the result, and we have always some formulas for the covariance, okay, for the covariance of the limiting field. Okay, so what is important about the proof? Yes, I have time. So let me just explain you what are the role of choosing the space of test functions. Okay, first thing is that we have to choose a space of test functions. So in our case now, we are in this space here. Okay, there's something extra, but just think about these conditions. So we cannot impose many things on the functions, otherwise we are, let's say, throwing away the boundary conditions, right? If you put, for example, functions with compact support, you kill the boundaries. So you have to be careful. You have to ask some conditions on the test function to have uniqueness, and you have to control some martingales. So usually the idea is that it's very similar to hydrodynamics. You prove tightness, and you characterize the limiting point. So let's look at the characterization of the limiting point. You associate to the density fluctuation field. Let's say you apply Dynkin's formula and you have this expression here. So this guy is a martingale, and now we have to compute this, I mean the action of the full generator in the density field. Okay, you do a very long computation and you get to the end at this expression here. So this guy is very good because this is exactly the y field applied to the discrete Laplacian of h. So let me, I have no more, can I erase what? Can I erase everything? Yes? Yeah? So now I want to show the following. My goal, okay, I'm hiding a lot of things, but the goal is to write this, as this. And whatever you find extra, it has to vanish, okay? That is the goal. So we do the computation, we look at the action of the generator, the bulk dynamics plus the boundary dynamics, and we find all these terms. Here it's fine, because this is exactly that guy, but we have these extra terms. So this is multiplied by the value of eta at 1, the occupation site at 1, and the occupation site at n-1, the guys which are close to the boundaries. And now you see that if I make this choice on the test functions, I immediately kill these terms. Right? You just do some Taylor expansion, and you see that what is remaining, it goes to 0 with n. Okay? So this is good. We can close the equations, and okay, we can close this equation here, but we still need to prove tightness, and for tightness, this is what we need. So we need a bound on the correlation functions, not only at time 0, so sorry, here was the condition that I asked before. I asked 3 conditions on the initial measure: to be associated to a profile, the initial profile rho 0 to be close to this profile that I fixed, to the continuous profile, and some bound on the initial correlations. And I need this y, because if this is true at time 0, then the bound propagates at time t. Okay, so if I have the correlations to go to 0 of this order, then at time t they go to 0. And this is okay, and this finishes the proof. Okay, okay, finishes the proof, but this is what you need for the proof. Theta different from 1, so let's see what is different. So now I say I don't have any more this space of test functions. So for theta less than 1, I have these. Okay, I have more than these, but let's just think about these. And for theta bigger than 1, so this is the Dirichlet case, and I have these, h prime at 0, h prime at 1, and this is equal to 0. So this is the Neumann case. And then I say, okay, so what can we do? So this is the statement. The only thing which changes with respect to the previous slide is that now you have this. I erased it? Yes, I erased it. Okay. Let's say the weighted L2 space is different now. You don't see these Dirac measures that I mentioned before. Remember these extra terms? So we don't see them now. It's the only difference. And we can also derive these stationary fluctuations for whatever is this starting this stationary measure, this mu n s. So what happens now? So it's the same strategy. You look at the generator, let's see, you look at the action of the generator in the density field. You get this term, which is very nice. It is just the guy that we want. It is this integral here. But now we have these 1, 2, 3, 4 guys. Okay, so let's try to control these guys, these terms. Okay, so theta less than 1. My test function here, I have h at 1 over n. I know that h is 0 at 0, so what we can do is to sum or to subtract. It depends on the sign that I have. What do I have? I have a minus. Okay, so I sum. I have n3 over 2 over n theta, h1. I have a minus, I think, no? Yes, I have a minus. So I subtract. h0 is 0, so I'm not doing anything, right? I'm just putting h at 0. Eta at 1. Bar. Bar means that it is centered. So I'm removing the row ns at 1. Okay, so these bars here that you see are exactly these guys at site 1. Okay, so this is the discrete derivative. Okay, I use this notation. Divided by n. So you see the order of this factor is just n1 over 2 over n theta, right? Times the derivative of my function h times this guy. But above, I have something which is bigger. This is over the square root of n times the occupation site at 1, the centered occupation site at 1. So I need to show that this guy, the time integral, so remember that there is a time integral, so let me go back. You see there is a time integral here. So I need to show that, oops, the time integral of this term goes to 0, okay? So I'm going to show you what happens in the theta less than 1, theta bigger than 1 is the same thing. So I say the following lemma. Take x equal to 1, or n minus 1 is the same. And what we can show is that this integral, the variance of this guy, is bounded by this. So let's choose my c n theta equal to the square root of n here. So what do I know? I say, okay, so the variance of this, the variance of the time integral of this term, so let me write it here. So the expectation with respect to this measure mu n of the time integral of the square root of n, eta s1 bar, according to this lemma, it is bounded by cn squared. So I have an n times n theta over n squared. So you see, this is like, this is exactly n theta over n, which goes to 0 if theta is less than 1. Right? So we can kill this term for theta less than 1, and you can kill all the terms, you can close the field, and you can see only that term. That is the first term is going to be the term which survives. Okay? So this is the job to do, is to control these extra terms by computing these, oh sorry, I missed these guys here. Okay. By computing these, the L2 norm of these terms. Okay, for theta bigger than 1, it's something very similar. You just have to see that you don't have any more these boundary conditions on the functions, but you have these ones. So in fact, the bad terms are the terms which are in the third line above, okay? Okay, so now, oops, 5 minutes. Okay, so let me tell you, yes, just to finish, what are my initial measures? Okay, what do I need to impose on my initial measures? Okay, again, the same thing. I need to show that mu n, I need to start from a mu n which is associated to some profile. Here I need to ask the initial profile to be measurable and of class C6. I need this condition again. I need this empirical profile to be close to this profile rho 0 that I fixed with this order. And I need a bound on the correlations. Okay, and just a small remark, which is this. Usually when one tries to show non-equilibrium fluctuations, usually we need some bound like this. You need something uniform. You need that your correlations of your system to go to 0 with n, and usually with this order here, 1 over n. But here not only to kill these extra terms that appear in the martingale, but in tightness, we need something stronger. So we need also that the initial correlations of your system close to the boundary. So you see here, for example, x equal to 1, when theta is less than 1, you get n theta over n squared. So the correlations, they go to 0 faster than 1 over n. Okay? So the uniform bounds, they are not enough. You really need to control what happens close to the boundary. Okay? Okay, so these are the things that we impose on our initial measure. So, and why do we impose? It's the same story as before. If you have these at initial time, okay, you prove this, you prove that you have exactly the same bounds at any time t. Okay? It's a nightmare to prove this result, but it can be proved. So let me tell you what are, let's say, the ingredients to get these estimates on the correlation, these precise estimates on the correlation function, is that you have to find out a discrete, again, you have to find out a discrete equation for your function, write it down in terms of some generator of some random walk, which is, let's say, slowed at the boundary of your set. I know I did not remove, yes, I removed, yes, I erased it. It was written somewhere, but anyway. So you have this set Vn that I mentioned, and it's like you have a two-dimensional random walk, but the rates to go to the boundary here, they are of order 1 over n theta. Okay, so whenever I'm here and I want to go to the boundary, the rates are 1 over n theta and 1 everywhere. Okay, so I write my correlation function in this form, and then what I need to, okay, and something else, I need to also, this you have seen before, I need to find out a discrete equation for my discrete profile, for this what is called empirical profile, and I have again another operator which is basically the one-dimensional, I mean a random walk, 1, n minus 1, which is absorbed at the sites 0 and n, but the rate to go here is 1 over n theta and 1 over n theta. Oops. And what I need, what is important, so, okay, these are computations that you can, I mean, the equations are very ugly. You can compute stationary solutions to these equations, so you have all these ugly formulas. But what is important is that the time which is spent by this one-dimensional random walk, this random walk here, at the site 1 and n-1, it is of order 1 over n. And what is important when we look at the two-dimensional random walk is that the time that it stays in the diagonal, in this not exactly the diagonal, but you know, y equal to x plus 1, it is also of order 1 over n, okay? There is one tricky thing, is that, I said 1 over n, but my brain was thinking about something else, sorry. When theta is less than 1, this is the order of the time, n theta over n squared. So you see that for theta less than 1, this is even better than 1 over n. But when theta is bigger than 1, the time spent by the random walk here, it's very big. So we do not use the comparison. So we do not write this guy in terms of this the generator of this random walk, but with a reflected random walk. And then we just show that the time that the reflected random walk stays in these two sites is of order 1 over n. So these are basically the ingredients that we need. Okay? So I think I finished. I have 2 minutes. So I only going to discuss some, what can we do? What are we trying to do after? I mean, I was looking at this problem over the last, I think, 3 or 4 years. And it was very difficult to get to this bound on the L2 norm. So anyway, we solved it in the case theta greater or equal to 0. So hydrodynamics is finished, but fluctuations in the fast case, they are open. So this is my first problem that one can look at. Also, for example, if you take long jumps, so suppose now your system, your particles, do not jump to nearest neighbors, but they go and they jump wherever they want, okay, with the transition probability, P, which is symmetric, and we can impose more conditions. And more complicated boundary dynamics, for example, if you want to enter the system, but you only enter if you look, for example, at your neighbors. So your boundary conditions, they are not going to be linear. They start to be non-linear. So, okay, there are many other variants of this. So thank you very much.
Thank you. Are there any questions?
Do you think that you could relax the condition on the initial profile? I mean, you assume C6, but...
yes. That is a very good question. Yes, it's true. I can relax. So let me just explain to you why do I need the 6, it is somewhere here, right? C6. I can remove these if I ask this condition, 1 divided by n infimum with n theta. So if I start to ask that my initial correlations, they go to 0 faster, I can relax this condition. And this is something which is true for the stationary measure. We can check the, where is the, we have a formula for the stationary correlations. Yes, which is here, okay? So you can show, for example, that for the stationary correlations, you have exactly that bound. So if you start from that bound, asking that your correlations in the initial time, they go to 0 faster, then you can relax this condition on the smooth, on the C6, the initial profile to be of class C6. Okay.
Any other questions? If not, then thank you again, Patricia.